Welcome back to Physics 191. I'm Gerard Blanchard. This time, and next time, what we will be doing is to review the entire course of Physics 191. And the main idea that I want to get across to you is that there are very few concepts that we've applied to answer all of the questions that you've been asked this semester, and one procedure for applying those concepts to a question. The procedure is to make a model of the situation. Modeling the situation involves drawing a diagram, writing down all of the information in the question statement. Now, some of the information may be explicit. You may be given, you may be told exactly what the information is, or some of it may be implicit. You may have to infer some of that information from the question statement. For example, if you're told that an object is in free fall, then you can imply from that the acceleration is 9.80 meters per second squared straight downward. So that's an example of implicit information. You may be able to imply that an object starts from rest or stops or is finally at rest. So that's other information that it may be implicit in the question statement. And identifying implicit information is a skill. It's something that you practice. And so that's why we practice so much, so that you can gain that skill. The next step in modeling the situation is to identify the physical principle to apply. Now, there could also be more than one principle at work in a situation, but our principles, and there are 5 of them, are equilibrium. Now, that was an object that was at rest and remains at rest, or an object moves at constant speed in a straight line. Non-equilibrium meant that equilibrium didn't apply. Kinematic was where we had motion, we had acceleration, velocity, position, change in motion, change in velocity, change in position, and a change in time. Energy dealt with change in position and change in velocity. And momentum dealt mostly with collisions or explosions. And as I said, more than one of these principles might apply to a given situation. But whatever principles you identify that apply to that situation, then you write down their appropriate starting equations. For equilibrium, that would be Newton's first law, total force vector equals 0, or total torque is equal to 0. For non-equilibrium, that would be Newton's second law. For kinematics, we had our 4 kinematic equations. For energy, we had our work-energy equation. And for momentum, we had our momentum conservation equation. And so once you've written down the appropriate starting equations, you solve the equations. And that is our procedure, our strategy for answering physics questions. Let's go through all of these principles in detail and work out some questions just to give you just a little bit more practice. So our first type of situation is an equilibrium situation. And you identify an equilibrium situation because you have constant velocity, both in magnitude and direction, throughout the time period of interest. Now, that could also be constant angular velocity as well. And the general equations for equilibrium are total force in the x direction equals 0, total force in the y direction equals 0, and total torque equals 0. Now let's apply that to a situation. A 5.60 kilogram uniform door is 0.760 meters wide by 2.030 meters high and is hung by 2 hinges, one at 0.280 from the top and one at 0.280 from the bottom of the door. if the vertical components of the forces on each of the two hinges are identical, find the vertical and horizontal force components acting on each hinge due to the door. Now remember our procedure. Draw a diagram, list all your knowns and unknowns, identify this as an equilibrium situation, and write down your appropriate starting equations, and answer the question, please. Okay, let's draw our door. There's our door. It has a hinge here and a hinge here. Now our door is 0.760 meters wide and 2.030 meters high, and each hinge is 0.280 meters from the top and the bottom respectively, and we're told that each of the hinges exerts a vertical force and those are the same, so I'll write FV and FV, and it'll be the same FV. And the hinges will exert horizontal forces as well, and I anticipate that the horizontal force on the bottom, and I'll call that FHB for force horizontal bottom, will be to the right, and the horizontal force from the top, FHT, will be to the left. I could be mistaken, but if I am, then I'll just get a negative sign for one of those two numbers. Let me draw my x-axis and my y-axis. And I also have to apply the weight of the door. Okay. Now the weight of the door, I will draw in the middle of the door, and that would be weight is equal to mg. And I'm told that m is 5.60 kilograms and g is 9.80 newtons per kilogram. So the weight of the door is 5.60 times 9.80 is 54.88 newtons. Okay, now at this point we have gotten all the information that we can out of the question statement. We have to identify this as an equilibrium situation. And since the door is in equilibrium, it's at rest and it remains at rest, and it's not rotating, and it stays not rotating, then our equations are force total X is equal to 0, force total Y is equal to 0, and torque total is equal to 0. Let's go through these one at a time. force total X is equal to 0. Well, what are my forces in the X direction? I have force hinge bottom, FHB, in the positive X direction, and force hinge top in the negative X direction. So that would be minus force hinge top, and that must equal 0. So that tells me that the magnitude of force hinge bottom is equal to the magnitude of force hinge top. So they're equal in magnitude. But it doesn't tell me what that magnitude is. I'll have to get that from another equation. Force total Y is equal to 0 tells me that F vertical plus F vertical, because each hinge exerts an upward force F vertical, minus the weight, minus 54.88 newtons equals 0. So those are all my forces in the Y direction. And so that tells me that 2F vertical is equal to 54.88, or F vertical is equal to 27.44 newtons. So we've actually calculated the vertical force that each of the hinges applies, and in fact they each support half of the weight of the door. Now we are left with torque total is equal to 0. And in order to calculate torque, I will have to designate a pivot point. And my pivot point I will choose to make the bottom hinge. And that will eliminate a lot of my torques. The bottom hinge, none of the forces of the bottom hinge will exert a torque on the door if that's my pivot point. The vertical force from this hinge will not exert a torque because it's directly, that component of the force is directly in line with the pivot point. And so my only two torques will come from the top hinge and the weight of the door. So I'll only have two terms in my torque total. Okay, I'll draw a little separator here. Let's figure out which of these two torques, the force of the hinge on the top or the weight of the door, which of these exerts a positive torque. Remember that a positive torque is a counterclockwise torque. So if this is my pivot point, then the horizontal force of the top hinge will pull the door to the left, which would be clockwise around the pivot. So the top hinge will exert counterclockwise around the pivot. So that would be a positive force. So the hinge is pulling the door in this direction, which is counterclockwise or positive around the pivot. Weight is going would make the door rotate to the right, which would be counterclockwise. Which would be clockwise or negative. So the hinge is counterclockwise or positive, and weight is clockwise or negative. Okay, so the total torque is the force of the hinge at the top, times the distance that force is applied from the pivot. Now that would be the height of the door minus twice our 0.280. So that would be 2.030 minus 2 times our 0.280. That is this separation right here. Minus times the sine of the angle between this force and the direction to the pivot. and so that would be sine of 90 degrees, which is 1, so I'm not going to write that, minus my weight, which is 54.88 newtons, times, and what I'm going to use the perpendicular distance between this force and the pivot point. And the perpendicular distance is 1/2 of the width of the door. So, times 0.760 divided by 2. So this top number here is the height of the door minus the separation of the hinges from the top and the bottom. That gives us the separation of the hinges. And the perpendicular distance of the weight from the hinge is 1/2 of the width of the door, or 0.760 divided by 2. And all of that is equal to 0. So that tells us that force hinge top, and I'll go ahead and calculate out what this is. So force hinge top times 2.030 minus 2 times 0.280, which is 1.47, must equal this term right here, 54.88 times 0.760 divided by 2. And that would be 20.85. So force hinge top is equal to 20.85 divided by 1.47, or force hinge top is equal to 20.85 divided by 1.47 is equal to 14.2 newtons. And now we have the magnitude of force hinge bottom is equal to the magnitude of force hinge top, which would also be 14.2 newtons. And notice that I didn't get a negative sign for either my force hinge top or force hinge bottom. So I did anticipate the proper direction for force hinge top and force hinge bottom. So here's our door hanging from our two hinges. The top hinge pulls the door to the left and holds it up, and it pulls it to the left with a force of 14.2 newtons and holds it up with a force of 27.44 newtons. And the bottom hinge pushes the door to the right and supports the door. It pushes the door to the right with a force of 14.2 newtons and supports it with a force of 27.44 newtons. So that is what we were asked. The second type of situation that we encountered in this course are our non-equilibrium situations. And you recognize a non-equilibrium situation because the velocity of the object in question is not constant, so it's not in equilibrium. Our general equation for non-equilibrium situations is Newton's second law. The acceleration in the x direction is the total force in the x direction divided by the mass. The acceleration in the y direction is the total force in the y direction divided by the mass of the object. And the angular acceleration of the object is the total torque on the object divided by the object's rotational inertia. Now note that a situation can be mixed equilibrium and non-equilibrium. Now together with equilibrium situations, we often have kinematic situations. And a kinematic situation is a situation that deals with either acceleration or velocity or position and time. And our general equations for kinematic situations are 4. There are 4 general equations for x, and then we have the same equations for y and the same equations for rotation. For x, they would be the acceleration in the x direction is the change in velocity in the x direction divided by the change in time, or velocity x final plus velocity x initial divided by 2 is equal to change in x over change in time, or Vx final squared minus Vx initial squared equals 2ax times the change in x, or the change in x is equal to Vx initial times change in time plus 1/2 ax times change in time squared. And then we have exactly the same equations for y, the same 4 equations, and we have exactly the same equations for rotation, where we just change from our translational or our linear acceleration to rotational acceleration, translate from linear velocity to rotational velocity, and so on. So for rotation, we would have angular acceleration is equal to the change in angular velocity divided by change in time, angular velocity final plus angular velocity initial divided by 2 is equal to change in theta, the angle, divided by the change in time, and so on and so forth. You have the same set of equations for rotation as you do for motion in x and y. And remember that you choose your starting equation for kinematic situations based on what you don't know and don't need to know. Each of these equations leaves out either acceleration or time or velocity or position, and if you don't know that, then you will have if you don't know that and don't need to know that, then you can choose the equation that leaves out that factor. Let's do an example. When a Navy jet takes off from an aircraft carrier, it accelerates because the engines are at full throttle and because there is a catapult that propels the jet forward. The flight deck of a carrier is 90 meters long. An F-14 aircraft has a mass of 33,000 kilograms, and each of the 2 engines supply 27,000 pounds of force. The takeoff speed of the airplane is 160 miles per hour. And the question is, what is the force on the jet from the catapult? Now, I'll give you the conversion factors. If I hadn't given you the conversion factors, what you could do is look these up right in the front of your book. Both of these I took directly from the front of your book. 1 pound of force is equal to 4.448 newtons, and 1 mile per hour is equal to 0.4470 meters per second. Okay, now please set up your model. So you diagram the situation, list your knowns and unknowns, identify the type of situation that you're working with, and write down your appropriate starting equations. Okay, we'll have the jet move in the x direction. Here it is at rest, and we'll call that x is equal to 0. X initial is equal to 0. Vx initial is 0 because it starts from rest. T initial is equal to 0 because we can start our stopwatch wherever we want. The jet accelerates, and at the end of the time period, x final is 90 meters. It's moved 90 meters. Vx final is equal to 160 miles per hour, which we can convert using our factor of 0.4470 meters per second is the same as 1 mile per hour. And that gives us 160 times 0.447. That gives us 71.5 meters per second. So that's Vx final. T final, we don't know. So we don't know T final. And as it turns out, we don't need to know T final. We're not asked how much time does it take for the airplane to move that distance. The airplane accelerates in the x direction with an acceleration that we don't know. But we'll have to figure that out, as it turns out. And there are forces on the airplane. There's the force from each of the engines. So each of those is 27. So that would be 2 times 27,000 pounds. And I'll have to convert my pounds to newtons. And let's see, where will I do that? Okay. 2 times 27,000 pounds times 4.448 newtons per pound is equal to 2 times 27,000 times 4.48 gives us, that should be 4.448. 2 times 27,000 times 4.448 gives us a force of 240, and I'm going to just round it off there, 240,000 newtons. 240,000 newtons is the force of the engines. And then we have the catapult pulling it with FC. Okay, I think that we have gotten all of the information that we can from the question statement. We've listed all of our knowns and unknowns. And now it's time to identify the type of situation. Well, we're asked for the force. So, and the object is accelerating. It starts off at rest, but it doesn't stay at rest. So this is definitely a non-equilibrium situation. Or at least it's non-equilibrium in x, which tells us that the acceleration in the x direction is equal to the total force in the x direction divided by the mass. That's one thing that I did not write down, I think. Mass is equal to 33,000 kilograms. Okay, that was one bit of information that I had left off. Okay, so the acceleration in the x direction is the force from the engines plus the force from the catapult divided by the mass. So the acceleration in the x direction is equal to 240,000 newtons plus the force of the catapult divided by the mass of 33,000 kilograms. And that's all that we can do right now, because we have one equation with two unknowns. We have the force of the catapult, which is what we're looking for, and the acceleration in the x direction, which we don't know. Well, what do we do here? From your experience, you should know that We can find the acceleration by also treating this as a kinematic situation. We have an object changing its position over time, changing its position and changing its velocity over time. So this would be a kinematic X situation. And we choose our equation that doesn't have time in it because we're not interested in time. We're not asked about time. We don't need to know time. So we need our kinematic equation without time in it, which is Vx final squared minus Vx initial squared is equal to 2ax times x final minus x initial. Okay, so that would be Vx final is 90 squared minus Vx initial, which is 0 squared, is equal to 2ax times x final, which is 90, minus x initial, which is 0. And there we have an equation with one unknown in it. It's just ax. So we can find ax from this equation, and then we can use it in this equation to find fc. Okay, so 90 squared. Oh, I'm sorry. This is not correct right here. Vx final is not 90. Let's scratch that out. Vx final is 71.5 meters per second. So Vx final is 71.5 squared. I apologize for that. Okay, so now Ax is equal to 71.5 squared divided by 2 and divided by 90 is equal to Ax. And so 71.5 squared divided by 2 and divided by 90 is 28.4. 28.4 meters per second squared is equal to Ax. And now we can use this over here. So 28.4 is equal to 240,000 plus the force from the catapult over 33,000. And now we have an equation with only the force of the catapult in it. So we'll solve that. We'll multiply both sides by 33,000. So I have 28.4 times 33,000 is equal to 240,000 plus the force of the catapult. And so 28.4 times 33,000, and then I'll subtract 240,000 minus 240,000 is equal to the force of the catapult. Okay, so let's go ahead and calculate that out. 28.4 times 33,000 minus 240,000 is equal to 697,000. 697,000 newtons is equal to the force exerted by the catapult. So we can see that the force exerted by the catapult is 2 to 3 times greater than the force applied by the engines. The force applied by the engines was 240,000, and the force exerted by the catapult is 697,000. So the airplane needs that extra amount of force to get into the air, but once it's in the air, it takes less force to keep it airborne. Now, there were several special kinematic situations, and in these special kinematic situations, there was extra information that you could infer based on the situation. The first of these is a projectile situation. And how do you identify that? Well, you're near the Earth, and gravity is the only force on the object. So we also call this a free fall situation. So when you're in such a situation, you can also add the information that the acceleration in the x direction is 0 meters per second squared, and the acceleration in the y direction is negative 9.80 meters per second squared. So let's try an exercise of this type. A football is placed 45 yards from the 10-foot-high goalpost. The kicker kicks the football straight towards the goalpost with an initial velocity of 21 meters per second at an angle of 35 degrees above the horizontal. Does he score? I'll give you one more bit of information, and if I hadn't, you could find this in the inside cover of your book. 1 foot is 0.3048 meters. So the conversion factor from feet to meters is 0.3048, and a yard is 3 feet. I don't usually give you questions with English units in them, but this is the statement that came straight from the book, and you should also be able to convert from English units to metric units. So once again, diagram the situation, list all of the information that you're given or that you can infer from the situation. We will ignore air resistance. That's important. You have to infer that you can ignore air resistance. And let's figure out whether the kicker scores his field goal. Okay, here's our x direction and our y direction. We'll start the football off from x initial is equal to 0, y initial is equal to 0. Oh, and we're told that it has an initial speed of 21 meters per second at an angle of 35 degrees above the horizontal. So this would be Vy initial up here and Vx initial. And Vy initial would be 21 meters per second times, since it's on the opposite side, it would be sine of 35 degrees. And Vx initial would be 21 cosine of 35 degrees. So Vx initial is equal to 21 times the cosine of 35, which is 17.2 meters per second. And Vy initial would be 21 times the cosine, 21 times the sine of 35 degrees, which would be 12.0 meters per second. T initial is equal to 0. Okay, and we know that when an object moves, when an object is in free fall, it follows a parabola. And here it is at x final. X final is where the goalpost is, which is 45 yards from the kicker, so X final would be 45 yards. Y final, well, that's what we want to know. How high is the ball after it's traveled that distance? Vx final, we don't know. Vy final, we don't know. T final, we don't know. And the acceleration, AX and AY, we do know. Because the ball is in free fall, we're ignoring air resistance. So the only force on the ball is gravity. So we know that AX will be equal to 0 and AY will be negative 9.80 meters per second squared. And this is our Y direction. Okay. Have we gotten everything that we can? Oh, actually, I am sorry. X final is 45 yards. So we actually have to convert that to meters. And there are 3 feet in 1 yard. And 0.3048 meters in 1 foot. So I almost made a big mistake there by not converting to basic metric units. But we can calculate that now. 45 times 3 times 0.3048 is 41 meters, is equal to 41, and I'll actually keep another couple of decimal places, 15 meters. Okay, X final is 41.15 meters. So now we have gotten all of the information that we can out of the statement. This is a kinematic situation. So we have kinematic in the X direction and kinematic in the Y direction. Now, we don't care about the final X velocity and the final Y velocity. We don't need to know that. We do want to know what Y final is. So we're not worried about Vy final, but we do want to know the final height of the football. So we'll need the Y equation that doesn't have Vy final in it. And that is Y final minus Y initial is equal to Vy initial times T final minus T initial plus 1/2 AY times T final minus T initial squared. So that has Y final, which we're looking for, Y initial, which we know, Vy initial, which we know, T final, which we don't know, T initial, which we know, AY, which we know, T final, which we don't know, and T initial, which we know. So we could use this equation to find Y final if we can find T final from our X equation. So with our X equation, we want to find T final, and we're not interested in Vx final. And that would be the same equation. X final minus X initial is equal to Vx initial times T final minus T initial plus 1/2 Ax times T final minus T initial squared. X final is 41.15 2.15 minus 0 is equal to Vx initial, which is 17.2 times T final minus 0 plus, and since AX is equal to 0, this whole term is going to be 0. So I'm just going to write 0 to avoid confusing the issue. And what we see here is that we have an equation with just T final in it. 41.15 divided by 17.2 is equal to T final, or 41.15 divided by 17.2 is equal to 2.39. So it takes the ball 2.39 seconds to travel to the goalpost. And now that we know T final, we know everything we need to find Y final. So Y final minus 0 is equal to Vy initial, which is 12, times T final, 2.39 minus 0, plus 1/2 of negative 9.80, which is AY, times 2.39 minus 0 squared. And so we have Y final is equal to 12 times 2.39 times, plus 1/2 times negative 9.80 times 2.39 squared, and we get Y final is equal to 0.69, we'll call it 691 meters. So Y final is 0.691 meters. Now we need to know if that's greater than or less than 10 feet to know if the football cleared the goalpost. So we'll have to convert that with our equation of 1 foot is the same as 0.3048 meters, and that gives us a Y final of 0.691 divided by 0.3048, and that is Y final is equal to 2.27 feet. So, unfortunately, the football did not clear the goalpost and he did not score his field goal. Well, that was exciting. I didn't know what the answer would be, whether he would score or not. Unfortunately, he didn't. So that's all for this time. Next time, we will continue with our review of all of the concepts in Physics 191. Until then, think physics.